Thanks for coming. I'm Mike Franklin from UC Berkeley, and I have with me Matej Zaharia. And we're going to talk to you today about a couple things. We are both members of a group at Berkeley called the AMPLab. And AMPLab is a big data analytics research project. And I mean that in the good way of a research project, not the bad way. We've been developing a new software stack for big data analytics. And what we're going to do today is I want to tell you first a little bit about the AMPLab, what our mission is, how we're organized, what we're trying to do. And then Matej is going to come up and tell you about two specific pieces of software that we've already released and that are starting to see increasing use. Spark, which is a analytics framework, and then Shark, which is actually a port of the Hive SQL processor on top of Spark. And you'll see some more about those. So why don't I just jump into it? So I'm not going to spend a lot of time on this, but where's big data coming from? You know, it's click streams and logs. It's user-generated content, machine-to-machine sensors and things like that, and also scientific computing. These are all very different types of applications, but they all share the common issue that they're becoming more and more data-driven. And so what does this mean for technology? The answer is going to be, I'll give you sort of the standard answer first, and then I'll tell you the AMPLab answer. So the standard answer is the three V's, right? So volume in terms of more and more data that you have to understand, variety in terms of the fact that the data is coming from all sorts of places. Maybe it's not very well integrated, maybe it's not complete, maybe it's not 100% validated. And then velocity, the fact that you're getting more and more data as time goes on. And in the AMPLab, we're addressing all these problems, but our view is just slightly different. And really, the problem we're trying to solve is that we believe that if you're given more data, you should be happier, right? So if you're given more data, you should get a better answer. And that's just not really what happens in a lot of situations right now. And there's really two reasons why. If you think about data as sort of a table, it can grow in two dimensions, right? So you can get more records, right? You can get more rows of your table. And in that case, you end up with sort of a standard scalability problem. You have to be able to deal with more and more pieces of data to make sense of the information. Okay? But you can also, and as you start doing more and more analysis and growing your applications, you also get horizontal growth. You start getting more dimensions, more columns. And the scalability problem you get from those additional dimensions is very different. And what you end up with there is more of an inference problem. That as you collect more and more dimensions of data about more and more things, you can basically find yourself with evidence for pretty much any hypothesis you'd like to try to find evidence for. And so if you're not very careful, the quality of your inference can really degrade to the point where you're really not getting useful information out of the system. And so it is a big scalability problem in terms of dealing with the amount of data, and that's largely what we're going to talk about today in terms of Spark and Shark. But we're also focused on this inference problem and trying to understand how to deal with this problem of having just much more information about the things that you're trying to understand. And what this ends up happening, what this ends up turning into is really what you want to do is you want to navigate this three-dimensional space, which is you have some problem you're trying to solve or some decision you're trying to make, and you have a certain budget that you can use to do your data analysis. You have a certain amount of time to make that decision. And in order to make your decision with sufficient confidence, you have to have a certain answer quality. And these things all trade off against each other. You can spend more money and get a faster answer. You can be willing to accept an approximate answer and then get your answer cheaper or faster. And so the stack that we're building is going to allow users to make this trade-off in these three dimensions. And so our view of the big data problem is really these two things, that you want to be able to handle both horizontal and vertical growth of your data, and you want to be able to navigate this three-dimensional space so that people can get their problems solved. Now, the project that we're involved in is a collaboration of people at Berkeley with support from both the federal research organizations as well as a bunch of companies, which I'll tell you about. But I just wanted to mention, we were featured, some of you might know that in the spring, the White House announced a big data research initiative where they were trying to get a lot of the government agencies to start supporting more and more big data research. And the AMPLab was featured in the White House announcement as one of the first projects that was basically being funded under this initiative. And so we have a key role in this big data initiative. Our view is really that in order to make sense of this massive and diverse data, there's really three types of resources that you have, and this is where the name of the lab comes from. You have algorithms in the form of machine learning, statistical processes, and things like that. You have machines in terms of cloud computing and cluster computing. That's why we're here today. And then the P in AMPLab is people. So we also work with Amazon Mechanical Turk to do crowdsourcing and human computation. And the idea is that we want to build an infrastructure that basically integrates these three very different types of resources, again, to solve the big data problem that we just defined previously. So that's really our overarching goal, is to build this system that's not just a faster SQL system, although today we're going to convince you, hopefully, that we have a faster SQL system. But we want to really integrate these very different resources to solve really hard analytical problems, not just simple reporting. So we're making a few big bets. It is a research project. And our biggest bet is really the following, that even if you look at current NoSQL stacks and kind of line those up, say, compared to something that like a traditional database architecture from 10 or 20 years ago, you'll see that the organization of the software, the architecture, is really not that much different. That you have file systems, you have some sort of indexing, and so on. And our belief is that if you really want to solve this analytics problem, what you want to do is kind of start from scratch. And you really want to take state-of-the-art machine learning, state-of-the-art systems processing, state-of-the-art data management, get people that understand all these things together, try to get them to work together, and think about what would the system you could build if you could build things from scratch look like. Because that's one of the luxuries we have of being at the university, is we can do that, and it's kind of our responsibility to do that. And so we've structured the project in a way to get people with these very different backgrounds to work together, and I'll tell you just a little bit about how we do that in a second. The other thing is, it's a great time to be doing this kind of work. There are demands on systems that just aren't currently met, low latency being a big one. The idea that people, I'm a database guy by training. Database people are always taught that there's a right answer and then all the other answers are wrong. And that's really not true in a lot of scenarios. And so there's this ability to provide variable consistency. The fact that we have the cloud and we have elastic resources gives us tremendous ability to take on harder problems, scale up the resources when we need them, scale them back down when we don't. And really, there's just something that I haven't seen in the couple decades I've been working in this field, is just this tremendous willingness for people, even in mission-critical applications, to try new technology. And so it's a great time to be doing work, building systems, throwing it over to the fence and trying to get people to use it, because you get very quick traction. And Mateo will tell you a little bit about how we're doing in that regard. So there's a lot of opportunities that have come together to make this work feasible. And then the other big bet we're making, which is in the longer term, is, as I was mentioning, if you could bring people in through a system like Mechanical Turk or other crowdsourcing platforms, how do you use that very expensive, very kind of finicky resource in the best way, so that you can solve problems that current computers and current machine learning algorithms just can't solve. And so you want to build a hybrid system that can do this. So those are our big bets. And just a little bit about how we organized the lab in order to make this happen. We grabbed a bunch of people from a bunch of different areas, so databases, systems, networking, machine learning, and so on. And we actually put them all in a single room. So we had a bunch of these professors that I've listed up here all agree to give up their offices, move into a common space with about 50 grad students and postdocs, And the idea is to get these people who have very different interests and training and background to all work together to solve this hard problem. So we've set things up that way physically. We also set things up in a way where we have continuous interaction and collaboration with our industrial partners. And this is an example. I have a picture here of one of our biannual or semi-annual research retreats, where we get about 150 people together to talk about the current state of the project and the current state of big data in general. And so we launched at the beginning of last year. It's a 6-year project. Amazon Web Services is one of our major sponsors. That's one of the reasons we're here today, along with Google and SAP. And then a bunch of other companies have also signed on to sponsor the lab. So we currently have 17. There's actually an 18th company that's just joined. But we have very excellent interaction with these companies. We get a lot of feedback from them, and we have a lot of collaboration with them. So we're very focused on working with industry. We have this role that we're playing in the Big Data Initiative, which I told you about. And so we're really combining the government and industrial sponsorship in this project. And what we're doing, and that's what Matej is going to be telling you mostly about, is we're releasing a software stack, the Berkeley Data Analytics System, that we're releasing as open source software, trying to get as many people to use it as possible. Okay. So in order to do our work, let me just tell you briefly about a couple applications that we're working on, just to give you a feel, right? Because if you want to do research on big data, you have to have some big data applications. And so one of the applications that we've released is something called Carat. And what Carat does is it's a collaborative system for detecting problems with battery life on cell phones. So you download the Carat application. Let me build this out. It periodically reports back to the cloud about what's going on your phone in terms of what applications are running, are you moving around, what's happening to your battery. It collects that from all the people that are running the application, and currently we're up to about 500,000 downloads of this application. And then it figures out things that are going on in your phone. That it says, geez, you're running these applications. These have been correlated with heavy battery drain on these other devices. Maybe you should look at shutting that off. And then it'll tell you, if you do that, we estimate you'll get about an hour and a half of additional battery life out of your phone. And it also tells you, no, we're very careful so that it doesn't use much battery, but I guess it would tell you to kill itself if it did. It also will look for things that are happening on your phone that are anomalies and tell you, hey, you seem to have something misconfigured, maybe your Google Maps application needs to be reinstalled and so on. So, this is a great AMP application because, it's doing the crowdsourcing of the data, it's bringing things into the cloud, running machine learning algorithms on them, and then reporting that data back out. So that's one of our driving applications. Another one, which let me just build this out, sorry. Another one we're doing is we have a big effort on cancer tumor genomics. And the short story there is that the cost of sequencing genomes has been decreasing by about a factor of 10 every 2 years, which if you're familiar with Moore's Law, you'll realize is a lot faster than Moore's Law. So basically what's happening in genetics is that computers are getting slower and slower every year. And this is turning into, first of all, the ability to generate more and more data. So it is a big data problem. And it's also a big computation problem because you want to try to make sense of all this information. And so we're collaborating with people at UCSF, which is a medical school at University of California, and other places to bring together a lot of genomic information and to use big data technology to try to rethink what some of the basic processing algorithms for bioinformatics should look like. And Dave Patterson, who is sitting up in the front row here, is giving a talk on this tomorrow, and you should make a note of that and show up to that talk. He'll go into more detail on this. So, two very different types of applications, but they give you an idea of sort of the scope of what we're trying to do in the lab. Just to look at the current state of the stack, you kind of read it from the bottom up. So I kind of went with the Howard Johnson's coloring scheme here, but that's kind of the default. But basically we interact with a bunch of third-party stuff, which is the stuff that's in white. And then we've already released the orange pieces, and the blue pieces are things we're working on. And so basically, we're built on the Hadoop file system. We have the Mesos system, which we're not going to talk about today, which is basically a cluster virtualization layer, which is actually in use in a number of places. Twitter is probably the heaviest user of it. They're running, at last count, I heard about 2,500 machines on it in production. And it's an interesting system in its own right that you should look into. Spark and Shark, you're going to hear about next. Basically, it's kind of a MapReduce and Hive layer that's basically optimized for low latency interaction and for iterative computation. So a lot of machine learning algorithms need to go over the data continuously, or repeatedly. It's a really bad use case for Hadoop MapReduce, and we've optimized that. And so Spark and Shark have been released, and you'll be hearing more about that from Matej in a minute or two. We're building streaming versions of those so that you can not only get low latency queries, but you can also, for standing queries, get instantaneous answers as the data is flowing in. And Spark, we have a streaming version of it running. Once we get Shark running on top of that, then we'll have a streaming SQL implementation, which is a pretty interesting thing. On top of that, we start moving more into the machine learning realm. And so BlinkDB is a system that's meant for doing that trade-off I was talking to you about of answer quality versus time and cost. And so with BlinkDB, you can specify either a deadline for when you want your answer or a requirement on answer confidence, and then the system will run as long as it takes you to get you that much confidence. And so it's an approximate query answering system. On top of that, we're building something called MLBase, which is basically supposed to allow machine learning to be done by mere mortals. So you specify at a very high level in a declarative way what type of machine learning you want to do, and then the system underneath the covers does optimization, figures out which algorithms to run. And that's where we're going in the long term. So today we're going to talk about Spark and Shark. They're available. Mesos is available. The other stuff is coming. And our plans are to release it all as Apache or BSD. And so we want lots of people to use it. So basically where we're going, is really we're going up the stack. We're, trying to support sampling in a very efficient way. We're refactoring some things in the memory layer. Matej will tell you about how we exploit memory to get things to go faster. And so we're trying to make that a shareable resource. The streaming stuff I told you about, we're integrating graph processing into the system. That didn't show on that picture that I showed you yet because it's not quite put into the stack yet. And the declarative machine learning. And then we're, again, going to refactor the code so that we have some common libraries that you can use for machine learning when that's the right thing to do, for relational database query processing when that's the right thing to do, but yet have a common optimization infrastructure. So this is all stuff, it's a 6-year project. It's all stuff that's coming down the pike. So with that, I think what I want to do is ask Matej to come up. I'll give a little plug. There's our website. We try to keep that pretty up to date in terms of what's going on in the lab and what software is being released and what research projects are going on. We have user groups and meetups for the released software that Matej is going to tell you about. And then Matej will also, I'm sure, tell you how to get a hold of the stuff at GitHub and so on. So with that, Matej, why don't you come up?
Okay, thanks, Mike. Okay. Right, so I'm going to talk about 2 of the open source components we've released so far, Spark and Shark. And these are both projects that are actually starting to be used in production at a number of companies. And it's been very exciting to us to work with them and to work with the Hadoop community to build these projects. So let me start with Spark. So Spark is the AMPLab's parallel computing platform meant to be a next generation system in the line after things like MapReduce. And it achieves actually significantly higher performance than MapReduce in 2 ways. So one way is that it's designed to support in-memory storage and query processing. And this is important if you ever have a data set you're going over multiple times. So it's important if you have interactive queries you're asking about data, the low latency ones we heard about before. But it's also important in a lot of the more sophisticated algorithms out there today that are iterative. Things like machine learning, PageRank, and so on, that go over the data multiple times. The second thing that Spark adds is general execution graphs, so it's not just map and reduce. And these provide some substantial speedups even if the data isn't in memory. So as a whole, when you put these together, we found it can go about 100 times faster than Hadoop in real applications if the data is in memory, and also 2 to 10 times faster if it's on disk. And it is a new code base. It's not like a modified version of Hadoop, but it's designed to be highly compatible. So it supports HDFS, HBase, Amazon S3. It runs well on EC2, and is designed to be highly compatible with Hadoop. What is Shark? So Shark, Spark is great as a lower level thing for writing programs, but we found a lot of users want to run SQL. And Shark is a SQL engine that runs on top of Spark. And in particular, we did that by porting Apache Hive. So Apache Hive, as you guys know, is a very popular and mature SQL engine for Hadoop. And by porting it to run on Spark, we're able to maintain compatibility with data that's in Hive and with queries and user-defined functions and basically all of the complex features that are in Hive, but at the same time to make it run a lot faster. So the same speedups I was talking about before of up to 100x can also be had in Hive. And both of these components are open source. Spark has been around since about 3 years ago. We open sourced it in 2010. And Shark was released in April this year. And we've also been fortunate that they've been picked up and started to be used by a number of companies. So Yahoo, Cloud, Foursquare, Airbnb are just some of the companies that are using these systems. And we also have a growing user community. We run a meetup in the Bay Area. We have more than 400 people signed up for the meetup group now, and we have contributions from over 20 different developers. So we're excited to grow these open source projects with our connections at companies. Okay. So I'm going to go next into Spark itself, just show you a bit about how it works and what you can do with it. So Spark itself provides this high-level language-integrated API for writing data parallel computations, and it's available in Scala, in Java, and soon it will be available in Python as well. And one of the cool things is you can use it interactively from the Scala and Python shells. So you can also type all these queries interactively and really explore data that way. And it is the key way it works is it gives you these distributed collections that you can run operations on. They're called resilient distributed data sets, or RDDs. And I'll show exactly how that works. Okay. So in this example here, I'm going to show something you can do with Spark interactively at the Scala console. I'm going to show the examples in Scala to begin with. And this is, say you have a log file in Amazon S3 or HDFS, and there are some errors happening, and you want to interactively search for errors. So we have a cluster here with a master and a bunch of workers. So the first thing you type at the console is this. This is Scala code to create a distributed data set representing your file. And you can see it can read from HDFS. And this gives you one of these resilient distributed data sets, or RDDs. Next, you can apply different transformations on it that will happen in parallel. So I'm going to apply a filter. This is a collection of lines of text. I'm going to filter out the ones that start with error. And in there, that code in red is Scala syntax for a function, literal, or a closure. And you can call any Scala or Java function you want from in there. So it's any code you want. And so this gives us a transformed data set. Next, I'm going to do a map. Maybe they're tab-separated fields, and I want to pull out field number 2. And then I'm going to tell the system to cache the result of these transformations. So just the error messages, not the file itself, in memory. So far, these things have all just defined how we're going to build the data set. It hasn't actually run yet. And these things are all lazy. They run the first time you actually do a query on it. So let's do that next. So now I'm going to count how many of these error messages contain foo. And what the system will do then is figure out where the data is laid out across the cluster, this count is called an action, and send tasks to the machines to process the blocks. They'll each process their own block. They'll return back results as in a standard MapReduce, and they'll also build in memory any partitions of cache data sets they've computed along the way. So now those error messages are sitting in memory. So the next time you run a query on this, maybe foo wasn't the problem, I search for bar, the tasks are going to be scheduled according to memory placement. They'll hit the cache, and you'll get back results a lot faster. And to give you a sense of how fast it is, one of the tests we did is just full text, brute force search of Wikipedia on 20 EC2 nodes. It's about 50 gigabytes of data. And if you do it with on-disk data or with Hadoop, it takes about 20 seconds to scan this data set. If you do it with Spark in memory, it takes about half a second. So this is the speed up you get from putting data in memory. And you can imagine you can actually type these questions interactively at the console. We also scaled it up to doing a terabyte of data in about 5 seconds, and this would take 3 minutes if you just used Hadoop. Okay. The other cool thing about the RDD's model that we have is that they automatically provide fault tolerance. So I'm not going to go into a ton of detail on this, but basically Spark remembers how you built each data set, the filter and map we did here, and if one of the nodes goes away, it knows how to recompute that cache. So you can really view this as a fault-tolerant collection of items that you can just ask operations on, and it will work if your cluster scales up and down, if you remove nodes, if things fail, and so on. Let me show one other example, which is one of these iterative algorithms. And this is going to be just a prototypical machine learning algorithm. This is called logistic regression. So here you basically have data points that are labeled, like say you have spam and non-spam messages, and you represent them as vectors, and you want to find a line or a hyperplane that separates these vectors. So lots of machine algorithms are like this. And the way you do this is you don't know what the solution is. You start with a random line, and then you do what's called gradient descent, where you gradually improve it. And to do that, you do these iterations where each time you compute a gradient function, which is a sum over the points. You can view it as each point sort of pushing or pulling the line in a direction. And that gives you a direction to move the line in. So you get that. You've done one MapReduce job to compute that in parallel. You've moved the line. Then you do that again, and gradually the line will converge, it will converge to the right separating line. So lots of learning algorithms are like this. Here's what the code looks like in Spark. It's again, very simple code by leveraging Scala. So there's kind of two pieces. First, we load the data from HDFS using a map, and we tell the system to keep it in memory. And then second, we run these maps and reduces on it. We start with the initial line, which is a random line. And then we run these maps and reduces on it to actually do the gradient descent. And you can see, since this is an algorithm that goes over the data many times, if you can keep that data in memory, it's going to be a lot faster. So how much faster is it? This is a graph here that compares the results against Hadoop. So we also implemented logistic regression in Hadoop. This is, I think, 100 gigabytes of data on 50 machines. And so what you see is in Hadoop, every iteration is a MapReduce job, and it takes about 2 minutes. And that's to load the data from HDFS, do some processing, and write the result back out. In Spark, the first iteration is 80 seconds, but later iterations are only 1 second. And the reason for that is that the math in this job, like the dot product and stuff we were doing in there, is so much less expensive than the cost of I/O in Hadoop that really, if you're running this with Hadoop, you're spending more than 90% of your time just parsing and deserializing and reading data, passing it through all these layers. So if you can keep it in memory as a Java object in Spark, you can go substantially faster. And what's interesting about this is, lots of people run these types of algorithms on Hadoop, and you write it in MapReduce, it will scale linearly. It will look great, it will work on large volumes of data, but you're still paying, 100 times more CPU cycles, and in Amazon, 100 times more money than you actually need to run this computation. So we're excited to provide this platform as a better way to do machine learning. I've showed Scala examples so far. We also have a Java API that's out. Main difference in Java is you don't get to write closures yet, but you can pass in these little functions and you still get pretty concise code. And we're working on a Python one. You can find the development version, but that supports all C Python. It supports lambdas, and it works from the Python shell. So we're pretty excited to offer that. And finally, I've shown some sort of prototypical examples. We have a bunch of real applications as well, and they range from more traditional kind of business intelligence or analytics on Hadoop and Hive data to interactive queries on data streams or predictive analytics. There's a startup called Quantifying that's using Spark to do that. And we have research applications as well that push it in different ways, such as genomics. Just a picture, to show it works there too. This is one of the applications from Conviva, which is a large-scale video analytics company. They would run these geographical reports for who watched a video, and the initial version in Hive took about 20 hours on a 20-node cluster to process a week's worth of data. They implemented it in Spark, and because there's so much shared across the queries, they were able to run it in half an hour on just a 4-node cluster. And so this is again the kind of speed ups I was mentioning before that can apply in these real applications. Okay, so that now leads me to Shark. So hopefully, I've convinced you that Spark itself as an engine is powerful, and also as a programming interface is a nice way if you're a programmer to write applications. But a lot of data users are not programmers, or they don't want to sit down and write Python for every question they have. So they prefer to use SQL. And Apache Hive is great for that, but it's not a low latency system. So we thought, okay, can we take Hive and extend it to run on top of Spark? And luckily, the architecture of Hive made it possible to do this in a highly compatible way. So Hive consists of two pieces, really. There's the meta store, which knows about your tables and metadata. And there's the client, which actually gets the query, does some query planning, and submits it for execution. And then the execution happens on MapReduce and HDFS. In Shark, we keep the same meta store, and we just modify the client. So we changed the query optimizer and the query planner in the client to run on Spark instead of MapReduce. And we also added this cache manager that lets Hive load and keep tables in memory. And the cool thing about this is it's compatible with all existing Hive data. So with your existing Hive meta store, with your data in HDFS, S3, HBase, wherever it is, you can just run queries on it. We also did quite a bit more to actually optimize this to make this run fast. So one of the key things that gives Shark its speed is column-oriented storage. Just loading Hive data naively into memory is not good in terms of efficiency because Java objects and even the textual representation of Hive data in HDFS are a lot bigger than they need to be. You waste a lot of memory. So Shark automatically converts the records into arrays of primitive types. So for example, if your data has an array has an int and a string and a float in each record, you get one array of ints, one array of strings, and one array of floats. And that saves a lot of the memory that would otherwise be wasted with representation as Java objects. On top of that, it can also do column-oriented compression. And a lot of data sets are highly compressible when you look at them as columns. And so you can actually fit quite a bit of data in memory using Shark. We have some other optimizations in the engine as well. So one of the most frustrating kind of sources of bad performance in Hive is joins, and in particular, picking the number of reduce tasks and the join algorithm. Shark can do that dynamically at runtime. So as it runs stages of your query, it figures out how much data has come out at the end of the stage, and it says, OK, I'm going to do a map side join, and I'm going to use 10 reduce tasks versus 20, and so on. One of the other things it does as it loads data in memory, it computes statistics. So as kind of a rough index, it knows which files actually contain data from each time range and so on. It can prune partitions that aren't relevant to your query. And finally, it lets you control the layout of tables across nodes, which is one of the key optimizations in fast relational databases like Vertica and Teradata to make it run well on a cluster. And using it is actually pretty easy. There's really only one thing it adds to Hive, which is this ability to create in-memory tables. So if you want, you can run it on a standard table, or you can create these in-memory ones with table properties, memory equals true. And to do that, you just select which data you want to put in that table. So it's basically a view. And then you just run Hive against it. OK, so how fast does it go? I'm going to show some benchmarks that we recently ran comparing it against Hive. And for these benchmarks, we picked actually this data set and benchmark published a couple of years ago by Pavlo et al. And this was a big comparison of MapReduce against database systems. You might have heard about this. Mike Stonebaker was also involved in this, where they found that MapReduce was a lot slower than databases. So we wanted to see how fast is Shark on these queries. So I'm going to show 3 queries. First one is just a simple select. And I'm showing here, I'm showing Shark in memory, which is in green, Shark on disk, and Hive. And we can see Hive takes about 90 seconds. Shark on disk is already 5 times faster. It's only 18 seconds, and that's because of the more optimized execution engine. And then Shark in memory is only 1 second. It's that little green bar down there. So for these kinds of scanning queries, obviously putting the data in memory is going to help. Next query is a group by. So this involves quite a bit of network communication as well. But again, Shark offers some pretty significant speed ups. So here, when you go from Hive to just Shark on disk, it's about twice as fast. This is mostly because the execution engine has less overhead. And then when you go to in memory, it becomes about, I'd say, yeah, about 8 or 10 times faster again than what it was before. And again, there's a substantial benefit to actually doing these queries in memory. Finally, I'm going to show some joins. So this is one of the more complicated queries in the data set. I'm not going to try to explain what it is. But I'm showing, again, Hive here took about half an hour almost. And I'm showing 3 bars for Shark. One of them is just the default one on disk. Then we have the one in memory, which is the dark green. And then we have the one where I use that controllable partitioning of tables to lay out the 2 tables that I'm going to join in the same way so that the hash partition together, and that avoids a lot of network traffic. And so if you do that, you can go down to just 100 seconds. And these speedups in all these queries are similar to what you get with the really high-end, high-performance database engines today. And they come with the benefit of running on commodity hardware and all the fault tolerance that you get from Hive and Spark. So these are some of these benchmark queries. We also have some users that have tried the system out. 2 of the early ones are Yahoo and Conviva, and they report similar speedups to the ones we've seen in the queries. So in Conviva, they took some of their Hive queries, and many of these are just sort of aggregation, like the group by one I showed before. And again, they see speedups of up to 100x when the data fits in memory. And they also see substantial speedups even if it's on disk because of the more optimized engine. So I should also say, this is all open source, and we're excited to have more people try it out as well. So let me see. Yeah, OK, I have enough time. OK, so next thing I'm going to do, just to show you that this stuff is real, I want to try to show you a little demo of it as well. And then I think we'll just have time for questions. So let me try to switch to that. OK, still up. Cool. So yeah, so one of the key things we did with Spark and Shark early on is make them very easy to launch on EC2. And so I'm not going to show how that happens, but you can launch a cluster in about 5 minutes using a set of scripts that's very similar to EMR. And so I did that now, and I launched a cluster where I'm going to run Shark. This is a 20-node cluster, and I loaded a 50 gigabyte Wikipedia data set onto it. And this is the Shark shell in it, which is basically Apache Hive. So what I'm going to do first, I'm going to actually set it to run the queries on Hive, on MapReduce, instead of running them on Spark. So you can switch back to Hive in the shell if you want by just setting one of these properties. And I'm just going to see, OK, how long do some of these queries take using Hive? And I'm going to ask a query. I'm going to count how many Wikipedia articles. I have this table wiki2, which is all Wikipedia articles. Sorry. how many of these articles contain Berkeley? Because we just like to count these kinds of things at Berkeley. So let me just launch that on Hive. Don't worry, I can ask other queries too. And so, okay, so this is running, as I said, it's about 50 gigabytes of data and 20 machines, and it's submitted it as a MapReduce job, and it's going to go along and do that. So let's just give this a bit of time to finish. And it's going along, it's making progress. Yeah. Oh, there we go. I think it's almost done now. Let's just see. OK, so it finished. It ran a MapReduce job. And the answer was this thing down here, 13,000. 13,000 articles contain Berkeley. But it took about 40 seconds. So it's cool that we were able to do this on a big data set. But it's not exactly what I'd call interactive. So let's go back now and set the execution mode to Shark. And we're going to run the same query on Shark. And this data isn't in memory. It's just sitting in HDFS. So let's just run that. OK. So Shark is a lot more silent, at least in this mode. Basically, the log output can be either very verbose or very silent. But it runs, and it gives actually the same answer, which is always a good sign. But it only took about 7 seconds. So that's cool. That's OK. OK, I'm not actually done yet. OK, but thanks. So that's cool. That's a lot faster. Let me show you now how we can use the in-memory features also. So now I'm going to do, I'm going to create one of these in-memory tables. Not create, but create. Oops, I need to do this. Oops. Quite a bit of stuff to type for this. So I'm just going to select everything from the Wiki2 table and put it in memory. And this is, now it's actually loading that stuff into memory, and it's creating this cached table. So it's going along, and it took about 7 seconds to do that. And now let me ask the same question on the in-memory table and see what the answer is there. And so now we got the same answer in about 2 seconds. And a lot of that is just compiling the SQL query, actually. And just to show that we have other queries too, Berkeley was 13,000. Let's see how many contain Stanford. And it's only 11,000. So that's a great result to show right here. OK. So let me see. So that's a quick preview, seeing what Shark looks like. Oops, keep going backwards here. OK, so that's kind of what I wanted to show. Last thing I want to say is that it is easy to get started with these systems. So we've gone to a great deal of work to make them well documented and make them very easy to launch, especially if you're using EC2. And you can get a cluster like the one I had in about 5 minutes and start running your own queries. And so you can find out about Spark itself at sparkproject.org. You can find about the other systems at the AMPLab website. And I'd be happy to take any questions along with Mike.